Try it right now. Run your fingertips slowly across your own palm. Nothing. Maybe a mild pressure. But the squirming, involuntary, uncontrollable sensation that happens when someone else does the exact same thing, that is completely absent. The touch is identical. The nerve endings are the same. The fingers are human fingers moving across human skin. And yet, the result is totally different. That difference is not in your hand. It is in your brain. And what it reveals about how your brain works is one of the stranger discoveries in modern neuroscience. Your brain is not a passive recorder of the world. It is a prediction machine. Before you make any movement, before your hand even starts to move, your brain has already sent a signal to itself describing exactly what that movement is going to feel like. That signal is called an efference copy. It is a copy of the motor command your brain just issued, sent simultaneously to the sensory processing areas. The term was coined by the German physiologist Erich von Holst in 1954. He was trying to explain why fish could distinguish between the world moving and themselves moving through the world. The same problem applies to every moving animal, including humans. When the actual sensation arrives from your fingertips, your brain compares it to the prediction. They match perfectly. Predicted sensation, actual sensation, identical. So the brain does something that seems counterintuitive. It cancels the signal. Not because the sensation isn't real, but because it contains no new information. Your brain already knew it was coming. It was self-generated, expected, and therefore, in the brain's accounting system, largely irrelevant. This process has a name. Researchers call it sensory attenuation. Your brain attenuates or reduces sensory signals that it predicted itself. It does this constantly for almost every movement you make. Every time you move your eyes, your brain issues a copy of that command. Without it, the world would appear to lurch violently with each eye movement. The copy tells the visual system to expect the shift, so the world appears stable even while your eyes are moving. Every time you speak, your brain sends an efference copy of your own voice to your auditory cortex. That is why your voice sounds different on a recording. The version you hear in real life is attenuated, filtered by the prediction your brain expects. Every time you press your fingertip against a surface and then press back, your brain cancels most of the sensation of your own touch. The tickle response, however, is special. It belongs to a category of sensations that neuroscientists call nismesis and gargalesis. Nismesis is the light, crawling sensation, the kind that makes you shiver or twitch but doesn't produce laughter. Gargalesis is the deep tickle, the one that produces uncontrollable laughter, involves sustained contact, and seems to require an element of social interaction or surprise. You can occasionally produce kinesmesis on yourself. Light, feathery contact in the right spot can still produce a mild response. But gargalesis, the real, full-body, helpless kind of tickling, requires one thing the brain cannot provide for itself: uncertainty. When someone else's hand approaches your ribs, your brain cannot predict the exact timing, pressure, or location of the contact. That unpredictability is what the tickle response evolved to detect. Researchers believe ticklishness is an ancient defensive reflex. The areas of the body most sensitive to tickling, the ribs, the neck, the armpits, the inner thighs, are almost exactly the same as the areas most vulnerable to attack. A bite to the throat, a blade to the ribs, a grip on the inner thigh. These are the pressure points that matter in physical confrontations across almost every animal that experiences tickling. Tickling may be a system that evolved to detect light contact on vulnerable areas and trigger a protective physical response. The twisting, laughing, pulling away motion that defensive tickling produces. In 1997, neuroscientists Sarah Blakemore, Daniel Wolpert, and Chris Frith at University College London ran an experiment that demonstrated the efference copy mechanism directly. They built a robotic arm. Participants used a joystick to control the robot, which would then touch their palm with a soft probe. When the movement of the joystick and the touch of the robot were simultaneous, perfectly synced, participants reported almost no ticklish sensation. Their brain's prediction matched the outcome. When a delay was introduced, even a delay of just a few hundred milliseconds, the sensation became significantly more ticklish. The longer the delay, the more ticklish the touch felt. At a delay of around 300 milliseconds, the touch felt nearly as ticklish as if someone else had done it entirely. The brain's prediction window had expired. The touch arrived outside the predicted time frame. The brain treated it as externally caused, and the full tickle response engaged. Blakemore and her colleagues repeated this across multiple participants, with consistent results. The finding was not subtle. The shift from self-generated to ticklish was measurable, reliable, and tied directly to the timing gap between the motor command and the sensory result. That single experiment revealed something profound. The difference between your touch and someone else's touch is not chemical. It is not structural. It is purely temporal. It is a matter of timing. Now here is where the story gets genuinely strange. Schizophrenia. Patients with schizophrenia can sometimes tickle themselves. This was first documented in research by Dr. Sarah Blakemore and colleagues in the early 2000s. The same mechanism that cancels self-generated sensations, the efference copy system, is disrupted in schizophrenia. Some patients experience their own movements as externally generated. They feel as though their thoughts, their voice, even their physical actions are being controlled or produced by something outside themselves. And when that distinction between self and other breaks down at the neurological level, the brain stops attenuating self-generated sensations. The tickle cancellation fails. Patients with schizophrenia who were tested on the same tickling tasks as healthy controls reported significantly higher tickle responses to their own touch. The system that tells your brain which sensations you caused yourself, the system you rely on every second of every day without knowing it, is precisely the system that malfunctions in one of the most studied psychiatric conditions in history. Your inability to tickle yourself is not a quirk. It is a working demonstration of the brain's self-monitoring architecture. It runs silently, continuously, underneath every experience you have, separating what you caused from what the world caused, keeping your perception clean and your attention free. There is one more piece to this: laughter. Why does tickling produce laughter at all? Research by Dr. Robin Dunbar at the University of Oxford has proposed that laughter evolved as a social bonding mechanism. Tickle-induced laughter in particular appears in primates and appears to require a social context to function properly. You cannot tickle yourself to laughter, but another person can make you laugh uncontrollably with a feather on your foot. The laughter is, in a very real sense, a social response to a social stimulus. And the fact that it requires another person, that it literally cannot be triggered by yourself, may not be a side effect of the tickle response. It may be the entire point. The brain's prediction system quietly cancels self-generated experience to keep you functional. It filters your own noise so you can attend to the world around you. But some experiences are specifically designed to require another person to generate them. The touch that makes you laugh, the voice that surprises you, the contact in a vulnerable place that your brain cannot predict or cancel. Those experiences may be the nervous system's way of making you need other people. Not as a poetic idea, as a physiological fact. Try tickling yourself again. It still won't work. And now you know exactly why.